In this video, I want to talk about force diagrams, sometimes known as free body diagrams, and equilibrium. So we've learned about forces. We've learned that the acceleration of an object is the ratio of the total force or net force and the mass. So clearly, if there's no acceleration, if an object has no acceleration, it has no net force, no total force, and that situation is called equilibrium. So let me put that on the board. Not that the word is so important, but the idea that if you have no acceleration, you can take it to the bank that there's no net force. Condition of a system in which the net force is 0. All right, so anything that's not moving has a net force, the force of 0, whether it's a chair in the middle of a room, a ladder leaning against a wall, a car in a parking lot. All right, now there's situations where something is moving and it's still in equilibrium. All right, for example, imagine a asteroid or a spaceship moving in a straight line through empty space. Okay, it has a constant velocity. If it has a constant velocity, there's no net force, so that's also equilibrium. All right, think about a huge heavy elevator and a cable lifting up the elevator with 10 people in the elevator. Okay, if it's being lifted at a constant velocity, that is also equilibrium. Now, you say, well, how could the net force be 0? Well, I'm not saying that there's no forces. What's happening is that all the forces are canceling. Gravity and the tension are equal and opposite in that situation. All right. Now, you will be asked to solve equilibrium situations where you've got multiple forces, and if you can identify that it's a equilibrium and you know that all the forces have to add up to 0, what I would suggest you do is make a picture. All right, so I'm going to do a couple of examples to show you how these things go. All right, so let's talk about a ladder leaning against a wall. All right, so let me make a quick picture. And the homework question, the exam question, whatever, or maybe you're an engineer and maybe there's a reason you need to know something about the forces in this situation. The point is, well, for whatever reason, if you're solving this, you want to understand the forces. It'll benefit you to draw a picture and then draw vectors, draw arrows identifying every force operating on the ladder. All right, so I'll go ahead and do that. We have gravity, so I'll just call that mg. Let's assume the ladder has a length, a mass m, and then we've got the normal force of the ground. Maybe I'll call that ng. We have the normal force of the wall, n wall, maybe n sub w. We also have to have a friction. I'll put a friction here, and that's the friction of the ground. And then we also have the friction of the wall. That may or may not be there. Maybe the wall is icy, so there's no friction. But we have to be open to that possibility. All right. So you see how I've identified all of these. Now, it's possible that you might know several of these vectors, the length and direction, but you might not know. There might be one that you don't know much about. Okay, and so what you can do is use the fact that the net force is 0 to solve for whatever you want. So let me show you what I mean. Here's the algebra equations you can set up. So we know that if the net force is 0, that means it's also true in every direction. So the net force, the x component of the net force is 0, and the y component is 0. Okay, so let's go ahead and set that up. So looking at my picture, what are all the horizontal components? Well, we've got the ground friction, and that's going in the plus x direction, assuming we've defined an xy axis like this. So we'll keep that way. And then the wall's normal is in the opposite direction, so we'll make that minus. And so both of those, that difference equals 0. So right away you can see that the only way that could be true is if the friction force of the ground is equal to the normal force of the wall, right? So a homework problem might be, suppose that the normal force of the wall was 50 newtons. Then what is the frictional force of the ground? Well, right away you would know that that has to also be 50 newtons. That's how the game is played. All right, now let's do the vertical. So we've got, what are the upward forces? Well, we've got friction from the wall. We've got the normal force up from the ground. And then the gravity is downward, so I'm going to put a minus mg there. And so there you have it. That would be what you could solve for this one. So for example, let's say we knew that the weight of the ladder was 150 newtons. And let's say we knew that the friction from the wall was, I don't know, 5 newtons. Okay, then using that, let's say we wanted to find the normal force from the ground on the ladder, so we can solve for ng. We would get n normal, n is in Nancy, ng. So shuffling this, the y component equation around, we would get that that's equal to mg minus the frictional force of the wall. So that would be 150 minus 5, so 145 newtons. All right, that's how that works. Now let me do another example for you, and then the other ones are going to be pretty much the same thing, so maybe one more to get the idea. This one didn't have any angles involved. Let me give you one that has angles. So the math is a little more cumbersome, but the concepts are still the same. All right, so let's say that we've got a inclined plane, and let's say that we have a box sitting on it, and let's say that the box is 80 kilograms, and let's say that we have a 30-degree inclination from the horizontal, and let's say that the mu for the, let's say there's some friction, let's say mu is 0.2, okay, and maybe we want to know how much friction there is. What's the frictional force holding up the box? Maybe we want to know the normal force. Whatever we want to know, the equations that you set up are all the same. So let me do that now. I mean, the force diagram will be the same regardless of what's missing. So what you do is, and I didn't, if this wasn't clear before, when you draw a force diagram, you only focus on one object, okay? There's forces acting on the box. There's also forces acting on the ground, the inclined plane, okay? If you have multiple objects, you'll have all kinds of forces operating on all kinds of stuff, okay? In a force diagram, you only focus on one object to not go crazy. And you think about what are all the forces pushing or pulling on that one object, okay? So there's gravity pulling down on the box, mg. There's a normal force, right? And there's a frictional force, okay? Now going to what I was saying about focusing only on one object, yes, the inclined plane is experiencing a push from the box, right? But we don't care about that for right now because that's not acting on the box. All right, so you can work out the geometry, and you'll see that if that angle was 30 degrees, then you have a right triangle here. So this has to be 60 degrees, which means, and then you have another right angle here. So this has to be 30 degrees. Okay, we're going to use that when we do our find the components. And also, instead of finding the components in the xy direction, or let me we can still call it xy, but the point I want to make is it might be easier if we define our xy axis like this. Let's see, that's an option. I'm just thinking if we do that, that will make certain vectors easier, but then it'll make the gravity be confusing. You know what? Just keep that in the back of your mind. You could do that, but let me... well, yeah, all right, let's go ahead and do that. I might as well show you everything that's possible in this example. All right, so for the x component, we know that the net total is going to be 0, x and y. All right, so quote unquote the x direction, the way I've defined it, we have gravity is going to be mg sine 30. Make sure you can see y. The triangle I'm using is this one right here, and I'm looking for that component right there. This is 30, okay, and that's why I get mg sine 30. All right, and then what other forces in the x direction? We got friction, opposite. All right, so that takes care of that one. So right away you could see that friction is the weight times sine 30 degrees. All right, and then in the quote-unquote y direction, we've got the normal force balanced by mg cosine of theta. All right, and so there you have it. So now if you wanted to calculate the friction is the amount of, it's mu times the amount of force pressing normal to the surface. So that's going to be the n, which from the, let me work this out. Let me focus on this equation right here. Okay, this is equal to 0. Looks like I didn't put that in before. Okay, equals 0. So that means that the normal is equal to mg cosine 30. Okay, so the friction is mu times mg cosine of 30, because that's the force pressing into the surface. All right, and so then you could make that substitution, and maybe maybe you didn't know the mass. Maybe this would, now you could use this to solve for what the mass was, because that's the only unknown variable. All right, let's go ahead and do that. So from the first equation, we have mg sine of 30 minus mu mg, actually no, I take that back. You couldn't solve for mass this way. It's going to cancel out. You'd need to know the, maybe for the y component equation, you need to know the normal, and then using the normal you could solve for the mass. So scratch that. But the point is, here is what you have so far. Okay. Actually, the way, so I gave you mu, and you could use mu with a lot of algebra. You could solve for the normal. Yes, the normal depends on mu. Probably, realistically, the way that this question would be asked is maybe you know the weight of the box and you want to find mu for the inclined plane, so you could solve for mu. That's another possibility. Okay, looking at the first equation, we could cancel out the m's. So that, and now we could also cancel out the g. Okay, so then mu is equal to, apparently in this example, tangent of 30, because we know that this tangent is sine over cosine. So I wrote 0.2. That's so. Oh, another way that this question could be asked is, you know that mu is 0.2, but you want to solve for the angle. All right. So if we didn't know mu, then we would know that mu is tangent of 30. Let's pretend that we knew. Another situation, let's pretend we knew mu and we wanted to know the angle. Well, then you'd have mu equals tangent theta. So theta is the arctan of mu, right? So I'm just trying to give you ideas for show you different homework questions that could be asked, different exam questions. But I hope you could see that the different questions, you'll just do different algebra, but the idea is always going to be the same. You balance the force components. You set the net force, each component equal to 0.